Hi students, welcome to the session on force on a differential current element placed in a magnetic field, right? So here what we are going to see, what is the amount of force experienced by a small current carrying element. We know that small current carrying element is the source of magnetic field. When such a current carrying element is placed in magnetic field, what will be the force experienced by it, right? So we know what is the force between the two charges. Now we will see what is the force experienced by a small current carrying element. What is the small current carrying element? Which is nothing but our wire. For example, you can take our wire is a small current carrying element, right? Differential means very small, right? So if the total length is L, the small part dl is a differential current carrying element, right? So we will see what happens when current carrying element is placed in a magnetic field. Let us consider a current carrying. This is a current carrying element. This is placed in a magnetic field, right? So whose length is L. Okay. So that is what we have to know. This cross indicates it is a magnetic field going inside the screen. That is negative x-axis. This x-axis is coming out of the screen. B, this cross indicates magnetic field going inside the screen minus x-axis. Right, current is flowing in the y direction. Please remember this is the current flow direction. So current flows along y direction, right? So these are all the conditions we make. So now if we keep like this, the force on a differential current element is given by dF. Differential means small current carrying. So we find a differential force. The force on a differential current carrying element is given by dF is equal to dq into V cross B. This is the force experienced, right? So that I can write as dq. V is velocity, q is charge, B is magnetic field. Velocity is distance per time, so dl by dt. Velocity is a vector, so we make dl is a vector. Time you cannot make it a vector. Length is in this direction, so we can make like this, and dl cross B. Okay, so this implies df is equal to dq by dt and dl cross B. Fine. So what happens is it implies df is equal to dq by dt is a charge per time current, right? That we know. I dl cross B. Fine, that was we know, right? So IDL is a current carrying element. So a force experienced by current carrying element, small differential current carrying element. That is only this part. I want total part means what is the total force experienced by L. We found what is the force experienced by this small part. So what I have to do? I have to integrate because next df I have to find, next df I have to find, next df. So and integrate. So integral df, left hand side integration means it will give f vector. Right hand side if you integrate it will be closed integral. Why it is closed integral? Because it is current flows in the closed integral, closed path only. So it is very important. Why closed? So f is equal to integral IDL cross B. So f is equal to closed integral IDL cross B. This is the force experienced by differential current carrying element placed in a magnetic field. Okay, so right, so if you make it I is a constant, take it outside, what is closed integral dl? Closed integral dl means it is dl means a small length, dl is a small length. Fine, it is dl1, next one is dl2, dl3, dl4, dl5, like that. Total dl will give total length, integral of dl will give total length. So IDL cross B gives I into L cross B. Fine. Integral dl is total length. Fine. So that is what. So what is the force? Ultimately, the equation is, this is the equation we have to use. IL cross B. Very important equation. So this is the force experienced by a current carrying element placed in a magnetic field. Okay. Now we will conclude so many. We will get so many information from this equation. Let us see here. Okay. So from this diagram, you know that current is flowing in y direction. This is the way current flows, y direction. So I is in y direction. right? So IL vector, current flow, IL vector, L is also y direction. So IL vector is in y direction. You see magnetic field is going inside the screen, that is negative x. So B is in minus AX direction, IL is in YY direction. So what will be the direction of force? We will see what is the direction of force. See, IL is in AY direction, B is in minus AX direction, AY cross minus AX equal to AZ. So force will be in AZ direction. So you see we have done it. Force will be in AZ direction. Pakka. Right? So this is the way you have to find the direction of force. That is very, very important. So when you keep your current carrying element like this, force will be in this direction. Current carrying element IL is in Y, magnetic field in minus X, force will be in Z direction. Right? This is important conclusion. Right? So the magnetic field, you see this magnetic field, very important point is this magnetic field is not produced by the current flowing through this conductor. See, we know that whenever current flows through a conductor, it will create a magnetic field. But we should not take that because we are going to work what is the force experienced by this current carrying element when it is placed in some other magnetic field. So this magnetic field is produced by external source, not by the current flowing through the conductor. That is very, very important thing. So whenever you do experiments like this, it should be what do you call magnetic field is produced by external current carrying external element. Second thing we are learning from this is we know F is a force, L is a what do you call line current carrying element. So similarly for line current, for surface and volume current we will write the equation like this. So F is equal to closed integral IdL cross B for line current that we have done now. What about for surface current? Surface we know it is KdS, right? KdS cross B. This is for force experienced by a surface. It is for line current, right? Next, what about force on volume? F is equal to JdB, right? So JdB. If you have any doubt how I write KdS is for surface, JdB for volume. If you have any doubt, please refer my video on Majeeth law. So it is volume current. Okay. So this is what three equations. First one is for line current that we derived. Similarly, it is second one is for surface and third one is for volume, right? And another important point to be noted here is we know F is equal to IL cross B. So F is a vector. It is a magnetic force. Already we studied Coulomb force is a electric force. F is equal to QE. This is electric force, right? Okay, now we see what is that? It's a vector. So what is the magnitude of F? So mod F is given by, if you take magnitude, you take a cross product. So F mod F is equal to F. L cross B is ILB sin theta. N cap will come. L cross B means N cap will come. If you take modulus, that N cap will be 1. Unit vector is 1. So ILB sin theta. This implies B is equal to F by IL or ideal. So whatever it be. So IL. So from this, what we are understanding, theta is there, right? So you see when current is placed along the direction of magnetic field, if I and B are parallel, right? In our experiment, we kept Y is in this direction, magnetic field will be in minus X direction. We hope you remember. Suppose if instead of this, if our magnetic field is also in this direction, magnetic field and the current also going in the same direction, what will happen? The angle between magnetic field and current will be 0. So this implies F is equal to 0 because theta is equal to 0. Yes, when I and B are parallel, right, you substitute this, F will become 0. Yes, so what is the meaning from here? From here we can understand that, right? when no force is exerted on a current carrying element if current flows along the conductor, along the magnetic field. That is very, very important. So if current flows along the magnetic field, the force will be zero. That's what we have studied. Force is perpendicular, right? So we have done. Next thing, if current flows perpendicular to the magnetic field, what will happen? If I and B are perpendicular, theta will be 90 degree. So F is equal to ILB, BIL. This is maximum value, right? So that is another important point. This is the magnitude of force, magnetic force. Then what is the direction? Because it's a force is a direction. We know force is given by IL cross B or ideal or IL, whatever it be, ideal cross B. You see, we have studied in dot product. If you take a dot product of two vectors A cross B, the resultant vector C will be perpendicular to both. So force is always perpendicular to both DL, current carrying element, and perpendicular to magnetic field. Already we proved force cannot be along the direction of magnetic field, right? So force is always perpendicular to the current carrying element and perpendicular to the magnetic field direction. That is very, very, very important, right? So magnitude of force, fourth point is the magnitude of force we studied, F is equal to BIL. What is that? It is magnetic force. What about electric force? F is equal to QE, right? You see, that is one beautiful concept. Here B is equal to force by IL or ideal, whatever it be. Ideal means it will be general, so we can write ideal. So what is it is force per current carrying element. See why I put IDL instead of IL. See, DL is small length I take, right, and it will be corresponding to Biot-Savart law and Ampere circuit law. That's why ideal. Even if you put L also, it's not a problem. So force by current element. Here you see electric field is given by force per charge. Beautiful concept, right? We have studied, right? The force experienced by a unit discharge is electric field. The magnetic field is force experienced by a current carrying element, right? So this is the electric field and magnetic fields are related to each other in a beautiful way, right? So that's all about this session. If you have any doubt, please ask me in comment section. I will clarify. Thank you.